Elon Musk just revealed Raptor 4, 10 times cheaper than Merlin at $100,000 per ton of thrust, producing 300 tons of power. SpaceX could save hundreds of millions per Mars mission. The industry is stunned. But here's the problem nobody's talking about. Even with 9 Raptor 4 engines, a Mars trip still takes 6 brutal months. 6 months of cosmic radiation, 6 months of health risks for the crew. What's the point of cheaper engines if astronauts can't survive the journey? So what's SpaceX's real solution to cut that time down to just 45 days? Let me break down what's actually happening here. Raptor 4 isn't just an incremental upgrade, it's a complete rethinking of rocket economics. Musk dropped the numbers on November 3rd. Raptor 3 costs somewhere between $250,000 and $500,000 per ton of thrust. That's already 2 to 4 times cheaper than Merlin. But Raptor 4, it crashes down to roughly $100,000 per ton. That's a 3 to 4 times reduction from Raptor 3 alone. Now here's where the math gets interesting. Starship version 4 will use 9 Raptor 4 engines, 3 sea-level, 6 vacuum optimized. Each engine pushes 300 to 330 tons of thrust. Total combined power? Nearly 3,000 tons. Enough to haul 100 tons of cargo to Mars. So with that kind of power at $100,000 per ton, you're looking at roughly $300 million just for the propulsion system on a single Starship upper stage. Sounds like a bargain for interplanetary travel, right? Wrong. That's only the engines. Add in the fuel, vehicle manufacturing, ground operations, and those 5 orbital refuelings you need. Each Mars mission climbs into multi-billion-dollar territory fast. But even then, even with all those extra costs, the leap from Raptor 3 to Raptor 4 could shave hundreds of millions off every single flight. Multiply that across dozens of missions, and you're talking about savings that dwarf most space programs' entire budgets. But cost isn't the only metric that matters. Musk mentioned back in late 2024 that when Raptor hits 300 tons of thrust at liftoff, which Raptor 3 can probably do, certainly Raptor 4 will, then Starship will have 10,000 metric tons of thrust at liftoff. That's 22.5 million pounds of force, almost exactly 3 times Saturn V. Actually, with 33 Raptor 4 engines, the real number could hit close to 11,000 tons. That's 16% more powerful than Raptor 3. And it's not just raw power. SpaceX is improving every performance metric. The vacuum variant could reach a specific impulse of 380 seconds. Chamber pressure on Raptor 3 already hits 350 bar, the highest of any operational engine today. Raptor 4 might push even higher. The real breakthrough? Simplicity. Raptor 1 weighed around 2 metric tons. Raptor 2 dropped to 1.6 tons. Raptor 3 came in at just 1.525 tons. Each generation gets lighter, more reliable, easier to build. SpaceX eliminated flanges and bolts, components prone to leaks, and replaced them with fully welded joints. They removed the traditional heat shield. Hundreds of small parts just disappeared. Production speed tells the whole story. Building a single Raptor 1 took around 11 days. Raptor 2 cut that to just 2 days, then down to 1 day. By May the 20th, Raptor 3 had already been spotted, less than a year after the first one debuted. Current estimates put Raptor 3 production cost at $600,000 to $500,000 per engine. Compare that to Blue Origin's BE-4, also methane-fueled, around 250 tons of thrust, slightly higher than Raptor 2. But in every other metric, it's not even close. The gap keeps widening. So when does Raptor 4 actually fly? If history holds, every new Raptor generation emerges roughly 18 months after the previous one's first flight. Raptor 3 should debut on Starship version 3 in early 2026. That puts Raptor 4 test videos around mid-2027, with actual flights by late 2027. Musk himself hinted Starship 5-4 could fly around that year. It lines up perfectly with SpaceX's mission roadmap: crewed lunar landings by 2028 under Artemis, then building sustainable bases that need far more capable vehicles. But here's the thing nobody wants to say out loud: all this progress, the cost reductions, the power increases, the production speed, it still doesn't solve the fundamental problem. Mars is 54.6 million kilometers away at closest approach. Even with Raptor 4's performance and a full orbital refueling, giving Starship about 7 to 8 kilometers per second delta V, you're still looking at a Hohmann transfer orbit. That's the energy-efficient route. It takes several months. 6 months minimum for most launch windows, 6 months of cosmic radiation exposure, 6 months of microgravity health risks, 6 months where a medical emergency means certain death because there's no turning back. Faster trajectories exist, 80 to 90-day transfers, but they need 10 to 12 kilometers per second delta V. That's beyond Starship's capability, even with full refueling. The limitation isn't just fuel mass. It's also the energy needed to slow down at Mars, which consumes massive amounts of propellant. So what's the answer? This is where things get controversial. Nuclear thermal propulsion, NTP. The concept isn't new. Research started back in 1955 with Project Rover, led by the U.S. Atomic Energy Commission. The goal was developing a nuclear-powered upper stage for ICBMs. After Sputnik in 1958, NASA took over and expanded it into NERVA, nuclear engine for rocket vehicle application. The technical results were impressive. Engineers developed 3 major reactor types: Kiwi, Phoebus, and Pewee. They achieved 4,000 megawatts of thermal power. Specific impulse hit 825 seconds, nearly twice that of chemical engines. A round trip to Mars became possible in just a few months instead of nearly a year. Compare that to Raptor 3. 6 engines producing about 18 meganewtons of thrust with 380 seconds specific impulse. Total delta V of 7 to 8 kilometers per second after full refueling with 1,500 tons of methalox. Enough to start the Trans-Mars injection at 4.3 kilometers per second, but not enough to cut travel time below 6 months. NTP changes everything. A fission reactor heats liquid hydrogen to thousands of degrees and expels it through a nozzle. Uranium isn't fuel that burns, it's a heat source. Hydrogen gets pumped through the reactor core, heats to several thousand Kelvin, then blasts through high-temperature alloy nozzles at extreme velocity. The key advantage: specific impulse of 800 to 900 seconds compared to roughly 450 seconds for the best chemical engines. That doubles exhaust velocity. For the same initial mass, an NTP system needs far less propellant or delivers much greater delta V. A realistic Starship NTP setup would use 4 to 6 mid-size nuclear engines. Total reactor output: a few hundred to around 1,000 megawatts of heat. Core temperatures over 2,000 Kelvin, hot enough to turn liquid hydrogen into high-speed exhaust. This system could perform short, powerful burns to boost speed quickly and long, steady burns to keep accelerating over time. Transit times to Mars, cut from many months to potentially 45 days in best-case scenarios. Professor Wong from Ohio State University, working on NASA-funded studies, put it simply: the longer you stay in space, the more health risks you're exposed to. If we can shorten that time, it would be a huge benefit. But the challenges are massive. Those giant hydrogen tanks need to stay extremely cold for weeks, very hard to maintain in space. Fuel lines and nozzles have to survive incredible heat and radiation. The crew and electronics need heavy shielding, likely boron compounds to block neutrons and gamma rays. Then there's the legal nightmare. Launching a nuclear reactor into space isn't something any government takes lightly. Starbase sits right next to the Mexican border. Even Florida launches are close to coastline. If something goes wrong during liftoff, the consequences go beyond safety. SpaceX could face massive lawsuits or lose launch approval entirely. And here's the technical problem everyone overlooks: thrust. Nuclear engines produce lower thrust than chemical engines like Raptor. They only show their advantage in space thanks to that higher specific impulse. For long-duration burns, they're unbeatable. But for liftoff, chemical wins every time. The solution might be hybrid. Use Raptor engines for initial liftoff, switch to nuclear propulsion in orbit. Starship could carry a separate nuclear module powered by liquid hydrogen, activating only after leaving Earth's atmosphere. Best of both worlds: strong chemical thrust to escape Earth, efficient nuclear propulsion for interplanetary travel. But that brings its own problems: added weight of two propulsion systems, integration complexity, higher costs, safety protocols multiply. NASA is taking it seriously, though. They're funding research into CNTR technology, centrifugal nuclear thermal rockets. Unlike traditional NTP using solid uranium fuel, CNTR uses liquid uranium inside a rotating cylinder. This maximizes fission reactions and significantly improves efficiency. Hydrogen doesn't have to be the only propellant either. Other materials could work, potentially extracted from asteroids or comets along the way. Refueling in deep space, traveling far deeper into the solar system than any chemical engine could dream of. So here's where we stand. Raptor 4 is a genuine breakthrough, 10 times cheaper than Merlin, more powerful than anything before it. Production costs dropping to $500,000 per engine. Flight ready by 2027. It will enable sustainable lunar bases and initial Mars missions. But for true deep space exploration, for cutting Mars transit from 6 months to 6 weeks, for making interplanetary travel safe enough that crews actually survive, chemical rockets hit a wall, even Raptor 4. The next leap isn't about better combustion or simpler designs or cheaper manufacturing. It's about fundamentally different physics. Here's the bottom line. Raptor 4 is a genuine breakthrough, 10 times cheaper than Merlin, powerful enough to make Mars missions economically viable. SpaceX will launch it by 2027, and it will change everything about lunar bases and early Mars exploration. But here's what the industry won't tell you. Even Raptor 4 can't solve the 6-month transit problem. 6 months of radiation, bone loss, and health risks. Chemical propulsion has hit its physical limit, no matter how cheap or powerful the engine gets. Nuclear thermal propulsion could cut that to 45 days. NASA is funding it. The physics work. But the engineering and regulatory challenges? Massive. We're talking about launching nuclear reactors from American soil. So we're watching two futures unfold, one with Raptor 4 enabling slow, gradual Mars colonization, another with nuclear propulsion making deep space travel genuinely safe, if the technology and politics align. Which future do we actually get? That's the question. If you want to track how this plays out, engine tests, policy changes, every breakthrough, subscribe to New Space Review and hit the notification bell. Drop your thoughts in the comments. Is nuclear propulsion realistic, or are we stuck with chemical rockets? And if this breakdown helped you understand what's really happening with SpaceX, hit that like button. We're covering the space race nobody's talking about. See you in the next one.